Have you ever wondered why a brand new computer feels just instant, while your old one takes forever? Well, it's not always about the main processor. There's a hidden hero working behind the scenes. Today, we're going to pull back the curtain on that hero, cache memory.
So really, what is the secret to a fast computer? Is it just about having the fastest processor money can buy? Or maybe cramming in as much RAM as possible? The answer is actually a lot more clever than that, and it all comes down to solving one huge fundamental problem in how computers are built.
Okay, here's the problem in a nutshell. Your computer's brain, the CPU, is an absolute sprinter. It processes information at mind-boggling speeds. But the main memory, your RAM, where all that information is stored, it's more like a long-distance runner. It can hold a lot, but it's way, way slower. This speed difference is a massive bottleneck. If that super-fast CPU had to wait for the slower memory every single time, your computer would feel like it was running through molasses.
And it's not just about raw speed. It's about how they talk to each other. You see, the CPU is needy. It wants tiny specific bits of data called words, and it wants them now. But main memory is more efficient sending over big blocks of data all at once. It's a total mismatch in both speed and style, and it's a problem that had to be solved.
So how do you bridge that massive gap? Well, you give the CPU a sidekick, a super fast, super smart middleman called cache memory.
So what is cache? Think of it as a small, exclusive storage area. It's built from really, really fast, and therefore expensive, memory. It's physically placed right between the speedy CPU and the slower main memory. And its entire job is to guess what data the CPU is going to need next and keep it ready. And here's the real magic. It's so good at its job that it creates this powerful illusion that your entire huge main memory is just as fast as the cache itself.
To really wrap your head around this, let's use an analogy. Imagine your CPU is a researcher working like crazy at a desk. The main memory is a gigantic library, full of every book you could ever want. Now, if the researcher had to run to the library for every single little fact, they'd get nothing done, right? The cache? That's the desk. You keep the most important, frequently used books and notes right there, within arm's reach.
So how does this desk actually work for our researcher? Well, the whole process really comes down to just two simple outcomes. You either have a hit or you have a mess.
A cache hit. This is the dream scenario. The CPU asks for some data, and bam, it's right there in the cache. In our analogy, that's the researcher just reaching over and grabbing the exact book they need off their desk. It's instant, it's seamless, and it means the work keeps moving at full speed.
But what if the book isn't on the desk? Well, that's a cache miss. The data the CPU is looking for just isn't in the cache, and that forces a timeout. The system has to take that slow walk all the way over to the main memory, our library, to find it. That delay, that time you lose, that's called the miss penalty.
Okay, so let's walk through it one more time. The CPU requests data. First, the system checks the super fast cache, the desk. If it's there, great, that's a hit, and the data is delivered instantly. If it's not there, that's a miss. The system then has to go on that slow trip to the main memory, grab a whole chunk of data, copy that chunk into the cache for next time, and then finally give the requested piece to the CPU.
Now, you can't just throw books randomly all over your desk and hope for the best, right? You need some kind of system to keep it organized. The better your system, the faster you find things and the fewer misses you'll have. Well, the exact same thing is true for cache.
The really big question for computer designers is this. When you bring a block of data from the main memory library to the cache desk, where exactly do you put it? This is called mapping, and there are three main strategies that computers use to figure this out. First up, we've got direct mapping. Now, don't let this diagram scare you. The idea is actually super simple. Think of it like having assigned parking spots on your desk. Book number 5 from the library can only go in spot number 5 on your desk. It's really fast to check because you only have to look in one place. But it's also super rigid. What if you need 2 different books that are both assigned to that same spot? You've got a problem.
So, on the complete opposite end of the spectrum, you have associative mapping. Let's go back to the desk. This is like saying a book from the library can go literally anywhere on your desk. Total freedom. It's incredibly flexible. But what's the catch? To find a book, you have to scan your entire desk every single time. And in computer terms, that means you need a lot of complex, expensive hardware to check every spot in the cache at the same time.
So if one is too rigid and the other is too complex, what do modern computers actually use? Well, they use this brilliant compromise called set associative mapping. This method basically splits your desk into a few sections, or sets. A book from the library can go anywhere it wants, but only within its assigned section. This gives you tons of flexibility without forcing you to search the entire desk. It's the perfect balance of speed and efficiency, and it's absolutely crucial for modern computers that are juggling a dozen different programs at once.
Okay, so that's all the theory. But what does this look like in the real world? Like inside the very computer or phone you're probably watching this on right now. Let's take a look. This table is awesome because it really tells a story. Just look at the Intel 8486 chip from 1989. It had a tiny 8 kilobytes of cache. That's barely enough to store a simple text file today. Now fast forward just over a decade to the Titanium processor. We're not talking kilobytes anymore. We're talking multiple megabytes of cache, all split into different levels. This just shows you how incredibly important cache became to keep pace with those ever faster processors.
And this is kind of what it looks like in practice. I know this diagram seems a little busy, but the big idea here is that modern CPUs don't just have one cache. They have a whole hierarchy of them. L1 is the smallest and fastest. That's like a sticky note on your monitor for things you need right this second. L2 is a bit bigger. That's your main desk space. And some even have a giant L3 cache that acts like a shared bookshelf. They all work together to make sure you take as few of those slow trips to the library as possible.
So if there's one single thing you take away from all of this, let it be this quote. Cache doesn't replace your main memory. It just works with it so cleverly that it creates this powerful and totally necessary illusion that your entire memory system is lightning fast.
And that kind of changes how you think about performance, doesn't it? The next time an app on your phone pops open in a split second, or a web page just appears, you'll know. It's not just the main processor doing the work. It's that silent, incredibly fast sidekick, the cache, doing its job perfectly. If you enjoyed this deep dive and you want to learn more about the incredible tech that powers our world, do us a favor and be sure to like, share, and subscribe to Tech Talk 101. Thanks for tuning in.